Actually, his question is that when I say high-rise building, what I exactly mean, how much height is considered high-rise. So, as you yourself have rightly identified that this is all relative. In a metropolitan city, for example, in you can say in London or in Bangkok, a 20-story building is considered a mid-rise building, right? So, the definition of high-rise building is relative, but you can check this CTBUH, Council on Tall Buildings and Urban Habitat, CTBUH. Just Google it and you will find very interesting statistics about tall buildings. This is an international organization which has several interesting case studies about tall buildings, and also they have a tall building competition, design competition. They select tall buildings of the year for each year, right? So, about tall buildings or high-rise buildings, they have several interesting documents and figures and statistics. So, please check that. The exact definition depends on how you actually classify buildings. For example, as a structural engineer, sometimes a tall building is classified as a building which have a significant contribution from second or third vibration mode in its dynamic response also. So, sometimes it is defined based on the dynamic behavior also. A low rise or a mid rise building is primarily governed by only one mode. So, you have already studied the mode superposition method or modal RHA procedure, in which you calculate the response of a structure as a sum of different vibration mode contributions, right? And if the first mode contribution is around 80 to 85 or 90% of the total response, then it is declared as a first mode dominant structure or a low rise building in case of buildings. But if second mode contribution is also significant, which means like 20%, 25%, which cannot be ignored, or third mode also, then we declare it as a high rise building or a building with multi-mode contributions in its dynamic response. So, different standards define this range even also, this how much should be the contribution of second mode in order to declare it as a multi-mode building or high rise building, right? So, similarly, the height definitions are also there. Different international organizations, they specify specific height also, and obviously they all are different. All these classifications vary. So, as I have said that in some contexts, even a 20-story building is declared as a mid-rise building. But for example, if we talk about our local scenario, Pakistan, we will declare it or consider it as a high rise. Similarly, it depends on the surroundings also. If you have an environment where you have all like 20-story buildings, several 20-story buildings, and there is one 40 or 50-story building, that will be called as a high rise relative to those 20-story. So, it depends on what classification you are using to classify buildings. You specifically mentioned about HAZUS. HAZUS is a methodology and a tool also to actually perform seismic loss estimation. Seismic loss estimation itself is a big area. Loss estimation, which means that, for example, if you create a particular earthquake scenario, that if tomorrow magnitude this much or PGA this much level of an earthquake occur in this city, what is the expected loss? So, you actually calculate how much will be the repair cost for all structures, how much will be the downtime, how much casualties, how much people will be injured. All these social and economic losses can be quantified, and this whole process comes under this seismic loss estimation umbrella, right? And HAZUS is one of the tools which can perform this seismic loss estimation. It is integrated with the GIS system, where you actually model all the buildings, the whole city, you can say, the exact population, all the essential and non-essential facilities, and then you create an earthquake scenario. And that earthquake, as a result of that earthquake, the program computes what will be the damage as a result of that earthquake, right? So I am not familiar with how HAZUS classifies different buildings. For the purpose of loss estimation, it classifies based on different categories, like based on the material from which those buildings are made, and based on their structural system, for example, masonry, RC, confined masonry, etc. So actually, when I talk about, for example, modal participation of second or third mode, I generally refer to the normal frame buildings. Depending upon the structural system, the modal participation of higher modes can be different compared to the normal frame structure. For example, if you make a structure which is all composed of reinforced concrete walls, its modal participations or modal properties all will be different compared to a frame structure, right? So mostly when I mention modal properties, I generally refer to the regular frame structures where most of the assumptions, like the lumped mass at story level, all those are valid, right? So if you have another structural system, you will see that the modal properties will be different. So it is possible that you have two buildings which have same height, but their modal contributions for different modes is different. One may be governed by only first mode, but the other may be governed by first 3 or 5 modes, right? So there is a criteria associated with the modal RHA or the response spectrum analysis, which is very close to the modal RHA in conceptually. There is a specific criteria in prescribed in different building codes that how many modes you should consider when you are performing modal RHA. So in our last course, actually I didn't mention that criteria. I just said that you can include as many number of modes as possible, so that first few modes can be added, like 4 or 5 modes, but there is a specific criteria, right? So we will discuss that criteria when we will be discussing the code based seismic design. So in last lecture we were discussing that in performance based design we specifically link the seismic hazard to the building performance level, right? So seismic hazard is defined as the probability of occurrence of a potentially damaging earthquake. So it is generally defined by a ground motion parameter, and one common example of a ground motion parameter is PGA, right? So you explicitly relate the PGA value with the building performance. You will be able to directly answer that at this PGA you will be having cracks in your structure or in your elements, right? So if I plot on y axis the hazard level, in this case for understanding simplicity, you can think of it as the PGA value, loading severity on y axis, and any response of the building which is telling us the building performance can be plotted on x axis. In this case, for example, any structural displacement, right? So as we have more displacement, the building is more vulnerable. So the vulnerability in general can be drawn on x axis, and the hazard level itself, which can be defined by any ground motion parameter on y axis. We will get a curve like this, that building will remain linear elastic up till certain level of hazard, right? So the displacement will increase linearly up till a certain level of hazard, but then if we increase PGA or hazard level beyond that number, the building's displacement will not follow linear trend, and at a certain level the building displacement will keep on increasing indefinitely with very low level of increase in the loading severity. So this will be the maximum loading which is the structure can sustain, right? Beyond which the structure becomes unstable, or it becomes you can say unsafe, it is no more functional, right? So this kind of a curve we can obtain if we perform the dynamic analysis at different levels of loading severity, or against the earthquakes having different levels of PGA, right? So we can get these points and plot this blue curve explicitly for a nonlinear dynamic analysis. If we use a linear structural model to perform this analysis, it will always follow, forever follow the straight line. But a nonlinear model will have the capability to capture this complete nonlinear trend. Now this kind of a figure is actually explicitly relating the hazard level with the building performance, right? So you can directly tell that if the earthquake of this much level occur tomorrow, you can expect some nonlinear effect. If an earthquake of this much level occur tomorrow, the building will remain intact, right? So you are relating hazard to the performance directly, right, using a nonlinear analysis. And this performance can then be converted into any other loss. For example, here you can see that the performance can be linked to any other indicator. For example, damage or loss is directly observable. Cracking, yielding, crushing of different elements will be directly observable. But you can also even calculate the number of casualties expected at different levels of earthquake, because your performance objective can be set in terms of these casualties also. The owner or client may express his performance objective in terms of this requirement also. Downtime for rehabilitation, obviously this is related to the economic loss. If there is a business center or commercial activity which is not you can say continued after an earthquake, discontinued, which means you have economic consequences. So on this axis, all of the other losses, rehabilitation cost, right, retrofitting consequences or impact on sustainability of community, even these kind of losses can be related to your building performance, right? So as I have told earlier that there are models available which can convert the building performance on top into any of these losses, right? And ultimately you can answer some of those questions which are explicitly asked from you as a structural engineer. How much you can say repair cost will be there in case of a particular earthquake, you can exactly calculate, right? So as I have said earlier that this methodology is primarily developed for seismic loadings, but any other loading can follow this idea. The idea is simple, right? That someone which is an important stakeholder of the whole process sets a requirement, and all you have to do is to follow that requirement to fulfill it, and you are allowed to perform any analysis, you are allowed to use any standards unless you can justify them, right? It depends on the hazard level of that site, right? So for example, in north part of Pakistan, we know that clearly the seismic hazard will govern the design, right? But in the southern part, depending upon the height of the building, the wind loading can also govern the design, right? So actually in those cases you have to plot the story forces, right? Wind loading forces and earthquake forces, and then compare them to actually see which will be governing the design, right? But there is a one small issue in this case also. I am not sure I will be able to explain that clearly or not, but I just give you a hint that the wind loading, the design philosophy against wind loading and the design philosophy against seismic loading, they are different. They have a very big difference, and that difference is that against the design level wind loading, we want our structure to completely remain elastic. No damage is permitted, right? We design based on this idea. But in the design level earthquake loading, we intend to have some damage so that the design can be more economical. And when I will explain the code based design, I will explain the source of that idea that we allow some damage under the design level earthquakes, and we rely explicitly on the ductility of the building and overstrength, and we don't rely on these things in case of wind loading, right. So the summary is that for design level wind loading, our design philosophy is that it should remain completely intact, it should remain elastic. But for design level earthquake loading, we allow some damage, right. We don't design our structure on the exact elastic design level wind loading. We design our structures on a loading which is lower than that design level, right. And we rely on the ductility and overstrength of the building to account for those reduction in forces, right. So this is a difference between the philosophies. So actually you should compare the reduced seismic forces, reduced after considering that allowable level of inelasticity, with the elastic forces produced by wind loading. So this is one difference in this comparison. So there are many cities in the world which have a significant wind loading and a comparable seismic loading also, and Bangkok is one of the example, the capital city of Thailand. Most of the high-rise buildings, they are primarily designed on wind loading because they were considered free from damaging earthquakes at their design stage, but later we came to know that seismic hazard level can also be significant in some of the cases, right. So in that case, both of the loadings should be considered for design. Actually, when you design a structure against wind loading to remain completely elastic, then you have to explicitly check the performance against seismic loading also if it is significant, because if your structure is elastic, under the earthquake loading it can develop more shear forces and bending moments compared to if it is explicitly designed for seismic action, right. So this is one issue associated with all those sites which have significant wind loading hazard as well as comparable seismic loading hazard, right. So it's not that you can simply ignore one loading and design considering that the other will govern the design, right. So you have to consider in totality. So therefore the complete load combination set prescribed by building codes include wind loading as well as seismic loading, right. So even if you think that some loading is lower than the other one, you cannot exactly predict the structural behavior prior to analysis. So some elements may be governed by another load combination, some can be governed by another one, right. So but overall both of them are lateral loading, their characteristics are completely different. Wind loading is exposure area proportional, seismic loading is mass proportional, their mechanics is different, right. In general, wind loading is far more complex compared to seismic loading, right, because it depends on many factors. So just check the empirical expression prescribed in different building codes to calculate the equivalent static wind loading. It has far more coefficients and parameters compared to the empirical formula to calculate equivalent static loading for seismic loading, right. So the seismic loading is governed by 3-4 parameters maximum, but wind loading you will see more than 10. One is accounting for the height of the building, other is whether it is located in a valley or a hill, different factors, right. So wind velocity is one of them. So therefore overall wind loading is far more complex compared to seismic loading. So let's see quickly what are some of the concepts which we will be dealing with in performance based design or in this course mostly. First of all, you might have guessed up till now is that we will check the building performance at more than one level. Building codes just prescribe the design procedure at only one level, and that is the design level, right. But in PBD we will analyze our building for for an earthquake level more than design and for an earthquake level less than design, right? And our expectation from the building response is different in both cases. For the earthquake level more than design, which we called as the MCE level, maximum considered earthquake level, which is defined for buildings as an earthquake having a 2% probability of exceedance in 50 years. This is the definition of MCE level. It is an earthquake having a level higher than design basis earthquake. Design basis earthquake is generally defined as 10% PE in 50 years. So if you reduce the probability of exceedance, actually the earthquake level is higher than that, right? So for MCE level, our expectation from the building is generally that it can undergo significant damage, but at least it should remain standing. It should not fall catastrophically. We call this performance level as the CP, collapse prevention, right? Significant damage, but it should prevent the complete collapse. And another earthquake level which is lower than the design basis earthquake, we call it SLE level, which is defined as an earthquake with 50% probability of exceedance in 30 years. It is a very frequent earthquake and a low level earthquake, lower than the design level earthquake. And our expectation from the structure is that at this earthquake level, the structure will remain completely serviceable. Therefore, we call it service level earthquake. So there can be some minor non-structural damage, but the building will completely remain functional, right? And the performance level mostly associated with SLE level is called immediate occupancy, IO, which means that the building will be available for occupancy right after the earthquake, right? Immediate occupancy. Then obviously multiple performance levels are checked and multiple seismic events are applied. As I have said, SLE and MCE level analysis, and may utilize nonlinear analysis. For service level analysis, since our expectation from the structure is that it will remain completely linear, so we may use, in most of the cases, we may use a linear elastic model, right, which we also use for design level earthquake. But obviously for design level model, we assume some of the things based on the building code, design building code, for example the crack stiffness modifiers, etc. For service level analysis, we will not be using those design coefficients, because the purpose of this analysis is not for design, it is the evaluation at a lower level earthquake, checking the building performance at a lower level earthquake. So all those design related things we will not do in our computer model. Same is for MCE level model, but that model will be nonlinear, right? For MCE level analysis, we have to construct a nonlinear computer model, and again the purpose of that nonlinear model will be to check the building performance at a higher level of earthquake. The purpose is not the structural design, right? So therefore all the crack stiffness modifiers and all those things, we will not use that. We will use only for those components in that model which are modeled as elastic. All those components which are explicitly modeled as non-linear, we will not be using those cracked stiffness modifiers, because the effect of cracking will be explicitly modeled in the computer model. So we don't need to account them using some factor, right? So we may use nonlinear analysis. Obviously for MCE level we have to use nonlinear analysis. For SLE level we may use if we want, but mostly from linear analysis we can also perform this evaluation. Detailed local acceptance criteria and element by element checking. This word acceptance criteria will be discussed again and again, so let's make it clear right now. In all of the course this term will be there. Acceptance criteria is the number which is acceptable to us, right? And whenever this word comes, please replace in your minds with the word capacity, right? Capacity. For example, your concrete in a nonlinear computer model will be modeled using a complete stress strain curve and not using the elastic modulus only, right? So for concrete material properties, the difference between an elastic model and inelastic model will be that for elastic model the concrete is governed only by a constant number called elastic modulus, but the same concrete in the same model, when it is converted into an inelastic model, the same concrete will be governed by a complete stress strain curve with all of its points, right? So E is variable now, stress and strain. Now this stress strain curve is the capacity of your concrete. This is an input in a nonlinear computer model. I will show you in the next classes that whenever you make a nonlinear computer model, you have to define a nonlinear concrete in that, right, for RC structures. Now there should be some markers on this stress strain curve which should be acceptable for client, which are corresponding to the performance objective set by the client. For example, the first performance objective, let's say for my building, is that I want all my concrete to remain linear at that first level of an earthquake. Let's call it, let's say, SLE level. For SLE level, I want all the concrete to remain completely elastic, right? So let me call it all concrete elastic. This is at SLE level. This is my first performance objective. For example, let's set another performance objective, second one, and let's say this is at DBE level, and I call it as some minor cracking is allowed, minor cracking. And the third is MCE level, and let's say my client says that you can allow significant cracking or significant you can say damage, but the structure should still remain standing. It should not degrade and fall down, right? So let me call it significant cracking. Now these 3, 1, 2, 3 are my performance objectives. Now I have to convert these statements into the acceptable level of deformation, and after the analysis I will check, actually the program will check whether the deformation caused by the applied loading at these 3 levels exceeded the acceptable number or not. Now let's convert it now. All concrete completely elastic means that you should maximum go up to this point, up till which the line is linear, right? So the strain corresponding to that is my first performance objective, strain corresponding to first performance objective. Similarly, after this point 1, the concrete starts getting softened, actually cracking started in compression, and let's say at this point some minor cracking has already occurred, right? So let me call this strain level as the strain level corresponding to my performance objective 2, and I know that beyond this point concrete will collapse because this is the peak point, right? So no one will be wanting to be at any point on this declining curve. So the maximum point can be declared as the strain level corresponding to this third performance objective, right? So now I have 3 numbers which are acceptable for me as a structural engineer because they are fulfilling the client's performance objective, right? So I know that if I apply an SLE level earthquake to my structural model and any strain in any concrete go beyond point number 1, performance objective is not met, right? So now I have some targets in terms of the required analysis results, right? Or you can say the maximum level of deformation, right? These maximum deformations which are acceptable, they are called acceptance criteria, right? As the name indicates, acceptance criteria, and they are actually 3 different capacities: capacity corresponding to elastic, capacity corresponding to minor cracking, and the capacity corresponding to significant cracking, right? So they are actually capacities corresponding to the requirement set by client, right? And they are in terms of deformations. For all the ductile components, they will be mostly in terms of deformations. So for material level, they are in terms of material strains. So I can say that my SLE level performance objective, my SLE level acceptance criteria is 0.0001, and then for second performance objective it is 0. Let's say 002 and then 003. These three numbers will be called as the acceptance criteria, right? So let's say that let's have some names for the requirements also, and in that case this all concrete remain elastic can be called as IO, immediate occupancy, then LS, life safety. There will be some cracking, some repair cost will be involved, but no loss of life, and the third one will be CP, collapse prevention. So if I call these three performance objectives as IO, LS and CP, actually these three performance levels IO, LS and CP, then these three numbers will be actually the acceptance criteria for IO, LS and CP respectively, right? So I can call this 0.001 as the strain corresponding to IO, strain corresponding to LS and strain corresponding to CP. Now I will give this complete stress strain curve in my computer model as an input, and I will also define these three markers on it. Strain corresponding to IO, LS and CP, I myself will give that these are the numbers corresponding to my requirements, right, at different levels of an earthquake. Then I will run an analysis at three different levels of earthquake, let's say, and after the analysis I ask the program that tell me all those elements which exceeded the IO level at SLE level earthquake, right? So program will color code all those elements based on their demand to capacity ratios and will directly tell me. Let me give you an example. Let's say that I run an analysis for SLE level earthquake, right? So which means that loading is applied, the program have calculated the actual strain level produced by that SLE level earthquake, right? And let's call that strain produced by the earthquake as epsilon U, right? Now after the analysis the program will color code based on DC ratios, and DC ratios will be in the form of deformations, not forces this time, right, because it is non-linear analysis. So epsilon U will be divided by epsilon IO. Epsilon IO I myself have given at the time of modeling, right? So the program knows what is the strain corresponding to IO, right? So it will divide epsilon U calculated by the analysis with the epsilon IO which I provided and calculate this ratio, and this is DC ratio actually, because epsilon U is demand imposed by the applied loading, and C is the epsilon IO which is capacity corresponding to a performance level, which is IO in this case. If this number is greater than 1 for different elements, it will check, for example, and if it is more than 1 for a particular element, which means it have crossed IO level at SLE level earthquake, it will be shown by a red color, for example, right? Similarly, if I run an analysis for DB level earthquake, and after the analysis I can color code my elements based on their DC ratio. So what program will do, it will take that epsilon U produced by the DB level earthquake divided by all three levels, epsilon IO, epsilon LS and epsilon CP. It will do it one by one. So actually the program calculates the DC ratios equal to the number of the performance levels, right? So if, for example, the epsilon U over epsilon IO is less than 1 for a particular earthquake level, which means that it have not crossed the IO level. If it is more than 1, which means it have crossed the IO level at least, then program will use epsilon LS as the capacity, right? It will divide that epsilon U over epsilon LS and if that number is greater than 1 again, which means it have crossed the LS level also, right. So on the same stress strain curve, the program can also plot the demand quantities. For example, it can tell you that the maximum epsilon u experienced at SLE level earthquake is, let's say, this one, right, and the epsilon u experienced at the MCE level is, let's say, this one, right. So if this number is my epsilon MCE, epsilon u MCE, and let's say this number is my epsilon u SLE, both of these performance objectives are not met, because I am beyond IO level at SLE and I am beyond CP level at MCE, right. So both performance objective 1 and 3 are not met for this particular design, right. So that's how I hope I was successful in giving you an idea that how we convert the analysis results into building performance. That first we model the components as an inelastic component. So we provide the complete capacity curve of that component. Let's say concrete is one material, we provide the complete stress strain curve, right. And on that stress strain curve, we also provide 3 markers or few markers to the program, which are acceptable levels at different earthquake levels, right. So program knows that at this much level of an earthquake, what is the capacity corresponding to that. So at the end of the analysis, it divides the demand with capacity in terms of deformations, right. So up till now you were only familiar with the DC ratios in terms of forces. For example, Mu produced by some load combination divided by the Mn, which is the moment capacity corresponding to that. But now in nonlinear analysis you will see that DC ratios will be in the form of deformations, right. The strain produced by the loading divided by the strain which is acceptable, maximum strain which is acceptable. So this is the DC Meyer in terms of material nonlinearity. Similarly, for each and every component which you make nonlinear, you define the complete capacity curve. For example, for beams, you define the complete moment versus rotation curve. For shear behavior of a particular element, you define shear force versus shear deformation. For materials, you define their stress strain curves, right. So the complete action versus deformation curve is provided as an input in the nonlinear model, and then program after the analysis check that in this capacity curve how much is the demand value, where it lies actually, right. So I will explain this concept of action deformation curves or relationships. One of the basic example of this action deformation relationship is stress strain curve, right, but that is applicable to materials. But for other actions like moment, you have a corresponding rotation. For shear force, you have a shear deformation. For torque, you have twist angle, right. So every action have a deformation, and the relationship between action and deformation is related by a complete action deformation curve, which is in general non-linear, right. For linear elastic modeling, we assume that it is linear, but actually it is non-linear, right. So we have the detailed local acceptance criteria. Element by element, we tell the program that this much deformation is acceptable and more than that is not acceptable, right. So we provide the local acceptance criteria, and then after the analysis, program checks each element whether it passes that acceptance criteria or not for a particular earthquake level, right. So you, after the nonlinear dynamic analysis, you can see each and every element's performance, right. And this can be extended to non-structural elements also. Non-structural elements can also be modeled in a structural model, and then their acceptance criteria can also be prescribed. Some of the non-structural elements are drift sensitive, some are acceleration sensitive. So their acceptance criteria is also in terms of drifts and acceleration, right. So the definition of seismic hazard in PBD is probabilistic. This we have discussed in detail in last session. So hazard is actually the intensity and characteristics of ground shaking that design is developed to resist. Previously it used to be deterministic, which means, for example, magnitude X earthquake on Y fault. For example, you have this site, and this is your, let's say, fault which is governing the seismic hazard at your site. The deterministic definition of seismic hazard is that you assume a maximum magnitude which this fault can develop, let's say magnitude 7, and you already know the distance between the fault and your site, let's call it R, and it is, let's say, 30 kilometer. Now using these two numbers, 30 and magnitude 7, you can calculate a maximum PGA which can be experienced at your site if this fault produce a magnitude 7 earthquake. And there are relationships which can be used for this kind of a prediction, and those relationships are called GMPEs, ground motion prediction equations. Previously they used to call as the attenuation models. If you plot them graphically, they will look like this. That distance R will be on x-axis, and any ground motion parameter, let's say PGA, will be on y-axis, and they will look like this, these lines for different magnitude, let's say M6, M7, M8, right. So these kind of equations, they are available in abundance in literature. They are called GMPEs, ground motion prediction equations, or attenuation models also they can be called. So using these kind of relationships, you can simply say that magnitude 7, 30 kilometer, right, it will produce this much PGA at my site, right. So if you actually perform this process, it is called deterministic seismic hazard assessment, right, DSHA, deterministic seismic hazard assessment, that you directly calculate or estimate a peak PGA number or peak ground motion parameter which is expected at your site. No probability of exceedance or no information about will this number will be exceeded in future or not, right. So one fixed number, magnitude X earthquake on Y fault. This process will give you a deterministic definition of hazard. So if, for example, I get a PG of 0.5 G, this is a fixed number in DSHA, right. So no associated probability of exceedance. On the other hand, we have now a probabilistic definition which doesn't have a fixed PGA. It depends on what probability of exceedance you want to define that PGA, right. So previously this deterministic definition was easy to understand, but there is a considerable uncertainty on how strong motion from such an event actually is, how strong that motion from such an event actually is, right. So you just consider the worst case scenario, closest fault, maximum magnitude which it can produce, and then predict the PGA number at your site based on these GMPEs, right. But in probabilistic definition, as we have discussed in last session, that we don't define PGA directly, fixed number. We say that there is an X% probability of exceedance in Y years, and based on these numbers, this definition, we have a PGA value, right. So for example, we can say that 10% probability of exceedance in 50 years, the PGA is 0.5 G. But if I convert or change it into 2% probability of exceedance in 50 years, the number will not be 0.5 G, it will be more than that, right. So we have that flexibility, or we have that chance to have different levels of earthquake depending upon our requirement. So the low intensity shaking occurs frequently. For example, if I say that 20% probability of exceedance in 50 years, what does it mean? 20% chance that this earthquake will be there in next 50 years. It will be exceeded in next 50 years, there is a 20% chance, right. So it is more frequent compared to a 2% chance or a 10% chance, right? Just think about SLE level, 50% probability of exceedance in 30 years. This is the definition of SLE, which means that if the design life is 50-60 years, it will come at least once, right, in the design life. So the low intensity earthquake is frequent, high intensity earthquake is rare, right? So 2% MCE level earthquake will be having a very low probability to occur in the design life of the building, right? So moderate intensity shaking occurs occasionally and severe shaking occurs rarely. So we define different levels now, not one fixed level but different levels. So it is now our choice. We offer different solutions at different levels of earthquake, right? For example, if we opt for designing our structure at SLE level, which is not a wise decision, by the way, that you are basing your design at a very frequent earthquake, right? So which means that there is a big chance that an earthquake more than this will occur in the design life, which your structure is not going to sustain because it is designed on a lower level, right? So generally acceptable level of design earthquake is DBE level, which is 10% probability of exceedance in 50 years. So we check each level separately, and our expectation from structure at each level is separate and independent of the other. And in order to pass the final design, all the performance objectives should be satisfied. If there is only one performance objective which is not met, the design is not okay, right? So independently, the SLE level performance should be acceptable according to the performance objective which you have set for yourself. For DBE level, separately should be acceptable, and then for SLE level, separately it should be acceptable. All three will be acceptable, then you will finalize your design, right? So they can be more than 3 also, right? This IO, LS and CP performance levels, they are the ASC 41 terminology, but actually the idea is more general. It can be any 5-6 performance levels, right? It can be defined in terms of cracking, yielding, downtime, repair time, repair cost, everything, social loss, for example. So the idea is general, but IO, LS and CP are kind of 3 templates which we give to, which these are the names or placeholders which we use for these damage levels or performance levels, right? But the specific statement given by the client or stakeholder may differ from these words actually, right? So traditional building codes, we know that they implicitly attempt to satisfy the objectives for one single earthquake level, which is the DBE level, design basis earthquake. PBD on the other hand investigates at least 2 additional performance objectives explicitly, right? This word explicitly is very important. This is actually the difference between code based design and performance based design, that the verification is explicit, independent of any particular provision. The designer can verify that that requirement is being met or not, and this is all because of the nonlinear dynamic analysis, right? Because it make us, you can say, it enable us to actually see the building performance at the design level. So one is service level assessment, and our expectation is that there will be negligible damage, and this is an earthquake which on average will come at least once in the design life of the building, right? So it have a return period of around 43 years. Actually it is 43 years according to the latest guidelines, but in different other references you may get a different number. So 43-year return period means that if you see this level of an earthquake spread along the history, on average this earthquake occur every 43 years, right? So return period doesn't mean that that in future 43 years it will come, it is necessary that it will come once. It is not mandatory. 43 simply means that if you see this level of an earthquake in history, if you have, for example, hundred of these earthquakes, and you have the whole span of thousands of years, if you divide that thousands of years with the number of this earthquake, you get 43, right? So on average, if you distribute this level of an earthquake in history, it occur every 43 years. But there is no guarantee that it will occur in next 43 years. It can occur like two of these events can occur on the same day, right? So there is no guarantee. It's just a number, right, associated with the previous data. So collapse level assessment or MC level assessment, it is generally performed for the MC level earthquake, and the return period for MC level is 2475 years exactly. Sometimes we call it as 2500 years, right? So this is a very rare earthquake. It is an earthquake which occur on average after every 2500 years. So you will be very unlucky if this occur in the design life of your building, right? So therefore we allow significant damage, because there is a very less chance that this will occur in your design life. So therefore we associate the CP level performance level with this MC level. CP means significant damage is allowed, but building should remain standing, right? In between these two level is the code level, and code level is DBE level, and the DBE level have a return period of 475 years. Sometimes we call it 500 years round off. So 500 years is the return period for design level earthquake. So building code set this level 500 years return period, right, in between the 43 and 2475. But this definition is for buildings only. As I have explained earlier, that if you want to design a bridge, you will not design for DBE level of buildings. The DBE level for bridges is 1000 year return period, right? So DBE level for bridges is a different level of earthquake, but DBE level for buildings is a different. Similarly for dams, DBE level is a different earthquake level. For dams, DBE is sometimes defined as an earthquake with 0.5% probability of exceedance in 50 years. I think this corresponds to maybe thousands of years of return period, right? So this number can be converted into return period. I'll explain later. So dams are defined for like 3000 or 5000 or 10,000 years return period, depending upon what guideline you are using for designing them, right? So codes level is somewhere in between service level and collapse level, in between. So we are having a negligible damage at frequent hazards and significant damage under extreme hazards, CP level at extreme hazard. So code is somewhere here, and more importantly, code is in between, but it doesn't provide explicit check, right? So this is now a summary. 50% probability of exceedance in 30 years corresponding to 43 year return period. This is the serviceability performance objective associated to that. Minor damage to structural, non-structural. DBE level 475 year return period, moderate damage. This is code level. So whenever code prescribe a PGA number, by default it is DBE level, right? Maximum considered earthquake, 2% probability of exceedance in 50 years corresponding to 2475 year return period. Collapse prevention performance level, right? Extensive damage is allowed, repairs may be required, and sometimes they may not be economically feasible, right? But structure should remain standing, no collapse. But there can be different intermediate levels also. This is just one template which I give you. There can be some intermediate hazard level and a corresponding requirement at that level, right? So there can be more than 3 performance objectives. So for PBD process, first earthquake hazards must be defined clearly, because they are different than DBE now. For PBD to be successful, both the client and engineer must be satisfied. Engineer is actually requiring that hazard is quantifiable and performance is quantifiable, right. So he should make sure that whatever is the requirement from client, it can be converted into some numbers, which is acceptance criteria, right. So that after the analysis he can explicitly check whether those numbers have achieved or not. For owner, hazard must be understandable and performance must be understandable. This is the challenge for structural engineer now. He have to convert the hazard definition into something understandable, and similarly the performance also should be understandable for owner, right. So he will not report the acceptance criteria to owner, he will report the building performance. So he will not tell that all the strains in concrete are less than 0.001. He will say that building is completely occupiable after an earthquake, right. So he will convert acceptance criteria into performance. Similarly, hazard definition, so he will not tell that this much probability of exceedance in this much year, he will simply say a rare earthquake or a frequent earthquake or a design level earthquake, right. So he will convert hazard definition into some understandable terms, and these IOLS and CP are actually the attempts to make performance more understandable, right. So now let's go to the very first slide where we actually discussed all that, where we actually started. Actually, that's how it works in most of the other parts of the world. That, for example, the real estate developers, they carry out the performance based design for their buildings, and they get the certificate for PBD, that now with a little more confidence and surety we can say that building will be safe. Now he will sell that building or those apartments or shops maybe 5-10% costlier than the conventional real estate developer, saying that this building is now checked for some advanced level safety analysis and it is declared safe for future earthquakes. So the owners will be happy to pay some amount more if they are given this surety. So the developer is happy, the PBD expert is happy, and then ultimately the owner is also happy because he have more confidence now. So it's a win-win situation everywhere, right. So actually when I say client, I doesn't mean one single person which is just standing there want his building to be constructed. Actually the performance based design is something beyond building code. So actually you require some people at least which have that desire to go beyond building code, right, unless the authority having jurisdiction explicitly prescribe that you should go from that process of PBD. Other than that, it is all about being more confident about the seismic safety of your building, right. So this is what when I mean by client mean any stakeholder which wants or which have this desire to have an additional information or additional confidence on the seismic safety of his building, right. So any decision maker, stakeholder or client, it can be building owner also, single owner, but mostly it is for, you can say, real estate developers or mostly the developers of high rise buildings. So their questions like, will the building be safe, can I use the building after the earthquake, how much will be the repair cost. Now although with more confidence we can answer these questions, because all of these questions can now be related to the amount of yielding, cracking, buckling and all those things which we can simulate using a nonlinear computer model, right. So these analysis results or building performance, structural performance can be converted into answers of these questions, right. So this is the real art where the structural artist is required, which knows that if this number is coming from nonlinear analysis, it actually means this. So I should tell this to my stakeholder or decision maker actually. And obviously in between this process, as I have explained earlier, that there is a peer review process which is a mandatory part of this PBD process, right. So since it is an alternate design philosophy, so there should be a third person who can check actually this whole process, right. So there is no building code behind you when you are performing this whole process. So you have to pass through a rigorous this peer review process also, right. This have to do with some overall, you can say, conceptual development of the design practice in a particular area. So generally, one of the motivations of performance based design is that it can result in cost effective design, mostly for high rise buildings, right. Let me give you an example. Let's say that you design a building to remain elastic at a PGA level of 0.5 G, right. So this is the code based design where you ensure that the building will remain completely elastic. Actually this is not exactly true, but let's assume it for the sake of argument that a building will remain elastic up to 0.5 G, which is the DBE level. Let's say DBE level earthquake, which is 0.5 G, the building remain elastic, right. Now what will happen, I mean, is there a guarantee that 0.6 G will not occur in the design life of the building? No guarantee. So if 0.6 G occur tomorrow, how this design is going to perform, which is actually designed to remain elastic up till 0.5 G. Ideally this design is not effective for 0.6 G, right. Now since you designed this building only for one earthquake level, you didn't check its performance at an earthquake higher than that design level. So you cannot say anything about how the design will perform if tomorrow 0.6 G will occur. Maybe the building will completely collapse, maybe the failure pattern is brittle, right, because you haven't checked explicitly, right. But now consider the second scenario where you design for 0.5 G, but you also check for 0.7 G and also check for 0.3 G, right. So now you know exactly the whole spectrum of hazard which can vary, how the building is going to perform, right. So imagine a situation where the intention of building code is not matching with the intention of that stakeholder. He is saying that I don't want my building to remain elastic at 0.5 G, I want my building to remain elastic at 0.4 G, and I want some damage to be allowed at 0.5 G, which will result in significantly cost effective design, right. So this is a flexibility which PBD offers you, and you don't compromise on safety, actually you focus on performance explicitly, right. So imagine the cases where the intention of stakeholder is not matching with the intention of building code. Those will directly tell you the effectiveness of this idea actually. For many buildings, these two intentions can match, but for high rise buildings mostly they may not match. The requirement of a stakeholder may be different than what a building code expects from a building. I give you an example from Christchurch earthquake in 2011, where most of the code compliant buildings were safe according to code's criteria, but they were not functional, and this resulted in a huge economic loss which was not acceptable to those building owners, right. So although their buildings were code compliant, but their desire was not fulfilled. Actually, unfortunately, we don't have any legal framework here which acknowledges PBSD as an alternate design philosophy. In the new building code of Pakistan, since it is taken from IBC 2021, and IBC 2021 have that escape clause which allows the use of alternate design philosophy if it is allowed by the authority having jurisdiction. So therefore, legally now we are allowed to perform PBD in Pakistan now with the enforcement of this new code. But obviously, the code based design still will remain there, right? It will mostly be used for conventional building design. For high rise buildings, where the conventional design philosophy is significantly have a very high cost, we can go for this alternate option. Now, this peer review process is exactly there, keeping that need in mind. Actually, some other third party validation is required in this whole nonlinear analysis and modeling thing. And lastly, it is not that you perform PBD and then give to client and he will implement and that's all. It still require approval from AHJ, authority having jurisdiction. In ASC 7's terminology, you have to have a legal framework which approves PBD as an alternate design process, right? So in our local context, I think we currently cannot perform it as an alternate procedure which is approved by some authority. It will be somewhat over and above the code based design. So because code based design is conventionally acceptable and it is acknowledged by our legal framework of building control, right? So code based design is mandatory, and on top of that, if you want to perform PBD for some additional checks and review of the existing design, you can perform that, right? But actually there should be a separate authority which should approve PBD also as an alternate design procedure, as an alternate to the code based design. Actually, there are few design firms which want this technology to be available to the clients or stakeholders here in our local industry, right? So they are working on their capacity building to adopt this technology, right? Currently, I myself am a very strong advocate of this philosophy. So I pitch this idea to many stakeholders, many building owners, real estate developers, the developers which are constructing 40, 50 story buildings in Pakistan. So initially they are interested, but there is some hindrance in this, some issues which are, you can say, which need to be addressed. First of all, the most important is the availability of a legal framework. They ask that we can perform this PBD thing and it looks very good, but who will approve it, right? There are systems available for that. I give you one example, that additional safety which you get or additional confidence which you get as a result of PBD, you show it to all the other stakeholders involved in that process, including the potential buyers of your property, right? So in our local context, what can happen is that someone can perform or pass through all of that conventional design process, and on top of that he go for PBD process also, but that will not be mandated by any requirement from local authority, right?